Okay, so this is a 2018 paper number 2, TMUA. You know the rules of this, I think. 20 questions, 75 minutes, non-calculator, it's multiple choice. Okay, so it starts off fairly simple with some nice basic differentiation. I turned that into a half, just like you usually would, then divided each term by x to the power of half with the 2 as well, then differentiated, of course, and then put in the value of 4. I changed this back to a fraction when I did, because now I can see it's going to be the square root of 4, which is 2, then cubed, which is 8. And likewise, this is 1 over 4 square rooted, which is 1 over 2. And then you just find your answer. So a nice, easy warm-up, that one. Question number 2, quite a few ways you could do this. I thought about combining these two fractions together. But then I thought, well, actually, if I'm just expanding this out 12 times, so I've written out 4 of them, but it goes on 12 times, and I'm thinking about taking a bunch of these and a bunch of those, and I think about expanding as bouncing around to here, to here, to here, or whatever. If I want a constant term, because there are no constants in the brackets, right? So if I want a constant term, I'm going to need 3 times as many of these guys as I bounce around as these guys. Because for every 3 of those, that makes a 1 over x to the 6, which will cancel with 1 of those. So I need 3 times as many of those as those. Now, if I'm taking 12 things in total, I'm taking 1, 2, 3, 4, and so on, for instance. If I'm taking 12 things in total, this is essentially just a ratio question, how do I split 12 into the ratio 3 to 1? Well, I do it by taking 9 of these and 3 of these, right? Because 9 of these plus 3 of these is 12 things in total, and 9 of those will cancel with 3 of those. So what I'm going to do is I'm going to take the term that's 12 choose 9, because I'm choosing 9 of these. So while you take this to the power 9, because I'm choosing 9 of them, and you take this to the power 3, because I'm choosing 3 of them, I also need the choose term. Now, I'm doing 12 choose 9 because I'm choosing 9 of these. I could do 12 choose 3, and it would be the same thing, and I'll explain that in a second. But I'm just going to do 12 choose 9 of this. Now, when I take this to the power 9, that's going to be 1 over x to the 18, which is going to cancel with this x to the 18, which is nice, and I'm still going to have a negative in here, because it's an odd number of negatives. Now, how do I work out 12 choose 9? Well, this is the definition of the choose function. You do n factorial over n minus k, k factorial. So I'm going to do 12 factorial divided by, and then 12 minus 9 is 3, and then k is just 9. And this is why I could have done 12 choose 3, because then it would have ended up being with k is 3, I would have got a 3 here, which lines up with that, and then a 12 minus 3 for a 9, and it would have lined up. Now, this is usually pretty easy to do without a calculator, because 12 factorial is just 12 times 11 all the way down. And that cancels with most of 9 factorial. All of that segment just cancels with that. So now I'm just left with this, which is fairly easy to do. I can even say, well, 3 times 2 is 6. 12 divided by 6 is 2. So all I'm left with is 2 times 11 times 10. And however you do it, you actually get this, which is B. And that's the correct answer. Lots of different ways you could have done it. Maybe combining these into one fraction would have been quicker. I'm not sure. But I like the logic that I use. I think it's good maths. Okay, if you're doing 2 journeys with different speeds, you don't just average the speeds like this. This doesn't work. Average speed is the total distance divided by the total time. Now, there is a funky formula you can use for this, but we're not going to need it. We can just think of it as being the total distance across the entire journey, so both journeys together, divided by the total time it takes. So if we're looking at this first one here, the total distance you travel is 100 plus 100, 200 kilometers. And the total time you're going for, well, if you're doing 50 kilometers per hour for 100, that means that took 2 hours. And this took 2.5 hours, because 40, 80, and then another half to make 100. So that's 4.5 hours in total. And I mean, you can double both of these to get 400 over 9, and then you see that this is not 45. You can check that by just trying to do 9 times 45. It's not 400. So this is a counterexample, because if you were to just do this formula, 50 plus 40 divided by 2 is 45, but this isn't, the average speed of this isn't 45, because this says no. So this is a counterexample. So when I take it, it's not because it's right, it's because it's a counterexample. Okay, let's do it again with this. So what's the total distance here divided by the total time? Well, the total distance is, well, 50 kilometers an hour for 1 hour, so that's 50 kilometers. 40 kilometers per hour, that's 40 kilometers. So total distance is 90. Total time is easily 2. So that actually works. So this formula, what this turns out is that this formula works if you go for the same amount of time across both segments of your journey. If you don't, then it doesn't work. But it does work if you just happen to do that. So this isn't a counterexample. This one down here is total distance is 80 plus 100. Total time is well, the time here is 80 divided by 50. The time here is 100 divided by 40. This is 8 over 5. This is 5 over 2, I guess, if you simplify. Put those together to get this. And then when you divide by 41, you know you're not going to get a nice whole 45. And likewise, you could times 41 by 45 to check that it's not that. But this is also a counterexample. Okay, cool. Question number, so the answer is F, I guess. You can also do a quick logic check against this being true. For example, if you walked to, well, no, let's say you drove to London from Birmingham. That might take you a few hours. And then let's say that you crawled back from London. Now that will take you quite a few days or weeks or months. And if you consider the average, if you considered your average speed across that journey going to and fro London, first in the car, second by crawling, if your average speed in the car was 70 miles an hour and your average speed crawling was half a mile an hour, your average speed isn't 35 miles an hour. Because if it was, that would be saying you may as well have just driven 35 miles an hour there and back, which I think we'd all prefer to do, than, despite the fact that driving 35 miles an hour along a motorway would be horrifically boring, we'd all prefer that than driving 70 there and then crawling back. Like, we can tell it will take much less time. So we can logically deduce that this is not correct at all, except in the case where the time happens to be the same. But anyway, I'm rambling. We've got lots of questions to do. Question number 4. Okay, so cos between 0 and 3 pi over 2 looks like this. And we're told it has two solutions for some value c. So the graph y equals cos of x equals the graph y equals c twice in here. Now that means to mean that the graph y equals c is down here somewhere, right? If c was up here, then sure, you'd get a second solution here, but that's outside of your range. So c must be between 0 and -1. Okay, now what does the graph cos of 2x look like? This is the graph of cos of x. Cos of 2x looks like this, is when it squishes in and repeats itself another time. Now it's pretty clear that the graph of cos of 2x has 3 solutions with anything between 0 and -1. But that's not what it's asking. It's asking cos squared of 2x. I'm just kind of getting to cos squared gradually. Now, this is cos of 2x, cos squared of 2x. Now, basically, what happens when you square a function is that all of these negative outputs, so right now cos of 2x, cos 2 of pi over 2 is a -1. But when I square that, of course, it's going to become a positive 1. And likewise, any negative output is going to square to become a positive output, because that's what happens when you square. So this graph is going to essentially be pretty much the same on top. It's going to squish down a bit, because when you square a number between 0 and 1, it goes down a bit. But that's not really relevant to me. But all of the negative aspects of the graph are going to be flipped over to positive, because these negative outputs multiplied by themselves give you positives. So the graph ends up looking like this. So it's tempting to say, oh, well, no solutions then. But just be careful here, because they've also squared c. And when you square a number between -1 and 0, just like when you squared these negative outputs of cos, your number, that should say a c squared, I'm so sorry, that c squared is between 0 and 1. So when you square a number between 0 and -1, it squares up to be positive, and you end up with 1, 2, 3, 4, 5, 6 solutions. And that should say a c squared, I'm so sorry. But yeah, question number 5. The two diagonals of quadrilateral Q are perpendicular. So if I just draw this square, the diagonals are perpendicular, I think. So that's kind of interesting. I mean, it's not. But anyway, consider the following statements. One of the diagonals of Q is a line of symmetry. Now, we do have lines of symmetry in my square. The midpoints of the sides of Q, so the midpoints of this make a square. Well, they actually do in my square example. So both of these happen to be true in this simple square example. But this is saying, are they always true? So whenever you see this, you want to think, well, can I come up with an example in which they're not? So what I'm going to do is I'm going to start by drawing the perpendicular diagonals. But notice how I've made all these lengths after the intersection all very different, because that means I can draw a very wild quadrilateral around them. And now I can see from this example here that, well, the line of symmetry thing is clearly not correct, because these are not lines of symmetry for my shape. So this is not necessarily true. The midpoints being a square, now this is harder to tell. With a computer it's fairly easy because I can try and wedge a square into here, and it's definitely not going to work. So this example kind of also disproves that. But you can do a few drawings to disprove this. Drawing a kite works, I think, as well. You put a rectangle in it. If you draw like if you make your diagonals just essentially a vertical and horizontal, just with this line going out much further, you end up with like a sideways kite, and you end up putting a rectangle between its midpoints. But it also, you can kind of see it with my example as well. Neither of them are true. Question A. Question number 6. Okay, so we've got an if statement. First thing we do with an if statement is we ignore everything that comes after the statement until we've dealt with the if bit. If f dashed of x is greater than 0 for all x. So when I find f dashed of x of these things, if they're negative for some values of x, I can immediately cross them out because this statement is not talking about them. They're irrelevant. If f dash of x is greater than 0 for all real of x, this is not greater than 0 for all x. Like if x is -1, it's just less than 0, right? It's -2. So the statement isn't talking about this. It's irrelevant. Likewise, when I differentiate this, also irrelevant because this can be less than 0. If I differentiate this, now I have a hopeful candidate because this is always positive, add 1 is still always positive. So the question might actually be talking about a function like this. So I'll leave it for now while I get rid of any other functions. Differentiate that to get -1, clearly irrelevant. Differentiate this is a little bit more tricky, but hopefully if you've done year 13 maths, if you haven't done year 13 maths, then maybe you didn't know this and had to look it up. But when you differentiate that, you get 2 to the power x log to base e, the natural log, I've just put that there to make it clear, of 2. Now that's a positive number, and this is always positive, because this is always positive, which means this isn't a counterexample to this statement, because this is positive, because this is, and so is this, and you're just multiplying two positive numbers, and this is positive as well, because this is always positive. So this isn't a counterexample, which actually means by method of deduction that this is, and I can prove it by just using, well, this is always positive, right, as we said, and if I use f of -1, I get -1 cubed is -1, -1 is -2 plus 1, and that's negative. So despite the fact that this is positive, this isn't, which means this is a counterexample to that statement. And actually, even if you hadn't have done year 13 maths and didn't know how to differentiate this, and it's rare in TMUA if you have to do something like this, you wouldn't have to anyway, because you could have just stopped here, worked out this bit and said, oh, that's a counterexample, I don't need to read on. So you actually didn't need this bit, but sure. Question number 7. So cool, I've taught this to year 7, so I know common difference 3 and first time 11 is a sequence that looks like that, and this is that. Some numbers appear in both sequences, so 17 I can spot immediately does. Let n be the 20th of the number. Now, I didn't know what to do on this question, so I just started listing out the sequence quite far, and I was hoping to find a bunch of numbers that would tell me something about the situation. And I did, right? 17 matches. The next one that matches is, I believe, 32, and the next one is 47. So those are my first 3 matches. Now, what do I notice about these? Well, there's a consistent difference, right? A consistent difference of 15. And that made sense to me because the lowest common multiple of the differences is 15, which means kind of every time this one rises by 15, this one also does. It just takes less time, which means they can match. If you have a matching term, 15 later, after you've added 3 to this 5 times and 5 to this 3 times, they'll also match. So that kind of makes sense to me. They turn up every 15. But I didn't think of that off the top of my head. I just listed. So sometimes just doing, something a year 7 could do is a good idea. It just gives you a feel for the problem. Now, this also tells me something. Now, if they turn up every 15, then that means that whatever the remainder when divided by 7 of this is, now the remainder divided by 7 of this is 3, right? Because 14 is divisible by 7, this is 3 above that. 28 is divisible by 7, so this is a remainder 4. And this is remainder 5 because 42 is divisible by 7. Now notice how the remainder is going up by 1 each time. And that makes sense because if they turn up every 15, that's 1 more than a multiple of 7. So these go up by a multiple of 7 and then 1 more. So the remainder stays the same as they go up a multiple of 7, 14. And then they go up 1 more and the remainder goes up by 1. This is very much like how if it's a Monday on January the 1st, then it's a Tuesday the next year of January the 1st, because 365 days in a year has 1 remainder when divided by 7, which means the day shifts forward by 1, unless it's a leap year. But that's why the days shift forward by 1. And likewise, the remainder here shifts forward by 1, which means that, well, the first matching one, remainder 3, second, remainder 4, third, remainder 5. The remainder is 2 more than the number of it. So the 20th matching term is going to have remainder 22, but remainder 22 is remainder 1 because it's 21 is divided by 7, so this is remainder 1. So yeah, B is 1. Okay, so we've got this kind of thing where we go up or down a few times. Now we have to start in the same place we finish, so we have to go up the same number of times we go down. So here we're going up 6 times and down 6 times as well. And this is called a valid code because it starts and ends in the same place and because it never goes below the horizontal plane. So that's the rule, is you're not allowed to go below, and you also have to be at the same place as you start and finish, horizontally speaking. If a code is written in reverse order, it's a valid code. Well, this ends with a down, so if I do this in reverse, I'm going to start with a down. And I'm not allowed to start with a down because that puts me below the profile. So that is not true. Oh, spoilers, I was meant to cross that out. Oh well. If U is a valid code, so if, again, this is a valid code, so let's just use this as an example. If each up is replaced by a down, the result is valid. Well, again, if I replace this up with a down, then I go down to start with. And I can't do that. So this is not true either. I can't do this. If U is added to the beginning of a valid code, so I'm going to add an extra U into here. And then I'm going to add an extra D to the end. Now that's important because if I add an extra U, I have to add an extra D to make it match and be in the same place as I finish. The result is always a valid code. Well, that's actually is correct, right? Because essentially, if you add an extra U at the start and D at the end, you shift the entire mountain up by 1, right? You leave everything in the middle the same, and you just shift the mountain up by 1 to start with, and then finish an extra down at the end to finish it. And of course, if you've got a valid mountain and you shift it by 1, it's still a valid mountain. So that's going to be fine. And that's the answer. Number 9, one of these spot the mistake questions. Couple of things going on here. Now, this looks fine to me. He's just factorized, so that's okay. Maybe the first thing I should do actually is just put these two numbers into here, because if either of them don't work, then I know this is not correct. Now, maybe that's not so helpful because I then need to identify where the mistake is. So I don't know. But anyway, number 1 is fine. Number 2, alarm bells are ringing because he's squared both sides. And the problem with squaring both sides is, let's take this. This has 1 solution. If I square both sides, suddenly I have 2 solutions, right? I can put in a -5 here and it's fine. So squaring does create solutions. So alarm bells have rung here. And the only way really to check whether you've invented a fake solution is to look at the end solutions and check whether they're both right, which essentially is what I said doing maybe at the start. But if you do put these in, I'm not going to bother doing it. But if you put both of those in there, they end up being fine. And it's just a bit of fraction work to make sure that you get that fine, but they both end up working. So actually, although squaring both sides does occasionally and often actually create phantom or false solutions, in this case it hasn't. Like sometimes it just doesn't. Like for example, here, if x equals 0, square both sides, you haven't created any phantom solutions there. So sometimes it's fine, and in this case it is. So let's move on. Now here, more alarm bells are ringing for step 3. Because he's cancelled this bracket with one of these 2x minus 1s, which means essentially he's divided both sides by 2x minus 1. And if 2x minus 1 happened to be 0, then he's divided by 0, and that's bad. So if, and maybe an example here, let's take this equation. If I factorize out and then divide, or essentially cancel both sides 2x minus 1, I end up with x equals 1. That should say, let's just change that, because of course, when you cross out this, you have a times by 1 there. Now, x equals 1 isn't a solution. Oh, sorry, it is a solution. It is a solution. 1 squared plus 1 equals 1 plus 1. But there's another solution here, which is minus 1. Minus 1 squared is 1, minus 1 is 0, minus 1 plus 1 is 0. So where did that other solution go? Well, it vanished when you divided this by x plus 1. So the solution we got did end up being valid, and these solutions we end up getting after all this are valid, but we've lost this x equals minus 1 solution because we divided by 0. So, okay, is this equals 0? So if 2x minus 1 is 0, then that means x is a half. And is a half a solution to this? And it turns out if you put it in it, that it is. 2 times a half is 1, minus 1 is 0, so this is all 0. 10 times a half is 5, minus 5 is 0, so this is 0. So he's lost a solution. These solutions are fine, but he's missed a solution. So it's one of these things, and the error was in step 3. I missed a solution, error in step 3, because he's divided by 0. So always look out for that. When I think I've done quite a few of these now, and the only mistakes I've ever seen are squaring both sides, dividing by 0, and then not looking for extra solutions when doing sine, cos, or tan. So always look out for those things. I mean, just quickly, we can figure out that this is all fine, right? Like, he's just expanded out and then moved it over, and then he's factorized fine. So this is all fine. Yeah, this is the answer. Question number 10. This question I hated. Let's just draw it. So what we're going to do is we're going to look at a graph that has, well, the line x equals a is this, let's just say. And let's think of the most simple graph we can that is reflective around x equals a. And I can think of this graph here, just a quadratic that has a solution at x equals a. Now, let's find, now if this is the point a, let's just pick a random point x there, and therefore say that this across here is f of x. So this is just some random point a, and let's call this just some random point x. Now, let's figure out where all of these things are on my picture. Okay, so a minus x, that's what happens when you take a and you take away x from it. Now, x is bigger than a, if a is here and x is here. So a minus x is negative. And f of a minus x, well, that's up here somewhere. It's where the line connects with the graph, just like this line connects with this graph to make f of x. Wherever this curve continues to touch this line, that's where f of a minus x is. And now x plus a, or a plus x, is over here somewhere, because they're both positive numbers. That's a, that's x. You add them together, you get over here somewhere. And now this looks like it could be the same. F of a minus x is up here somewhere. F of a plus x is up here somewhere. They look like they could be in the same place. And they actually are, right? Because the difference between these 2 points here is a distance well, we're going from a to a minus x. That's a distance of x. And the distance from here to here is also x. So you're traveling the same distance across this way as this way. And because this graph is symmetrical, remember I chose a symmetrical graph, that means that the outputs are the same. So this is fine. So yeah, I'm cool with that being okay. Now, this one I can deal with next. A minus x is over here, and clearly, according to my picture, that could be different to f of x, right? F of x is here, f of a minus x is all the way up there. So this can't be necessary and sufficient, because my picture just says my example says it's completely wrong. This is the most difficult one to deal with. Let's first find 2a. Now, if that's a, then 2a is over here somewhere. Firstly, I'll say that this, why am I saying this? Oh, sure, yeah, okay. This distance here is x minus a, let's just say. Because if that's x and that's a, then this is x minus a. Now, 2a is over here somewhere. Now, where's 2a minus x? Now, 2a minus x is, well, if this distance is 2a and this distance is x, 2a minus x is probably over here somewhere, right? Because it's all of this length minus all of this length, which leaves you with this kind of length here, but it happens over there. So this is maybe where 2a minus x is. And now what I'm saying is this in the same place as this? Now, according to my picture, it's not quite, but let's do the maths instead. Now, the reason I made this length here is because I know the distance across from here is just x minus a. Now, what's the distance across from here? Well, it's a minus, I don't know why I did that. That's irrelevant. This distance here is a minus 2a minus x, which, well, that's going to give you a positive x, that's going to give you a minus a, which is the same as this distance here. So because this is true, whereby if you have the same distance going across either side makes the same function, you've got the same distance between the line of symmetry and this as you do this. It's both distance x minus a, which means this is also true. And our answer is yes, yes, no. Quite a difficult question. I think it's the most difficult question on the paper. To me, at least. Maybe not to you. Okay, now, when I see this, I think, well, I don't know how to solve equations that have an exponential and a linear term in them. So I'm not going to. What I'm going to do is just try and graph this instead. What this is saying is if 2 to the x equals this is asking me where does the intersection of y equals 2 to the x and y equals mx plus c happen, right? So I can do this all graphically. So here's y equals 2 to the x, I think. Yeah, looks about right. And y equals mx plus c is just a line. And I'm going to look for whatever the question says. So the equation has a negative real solution only if c is greater than 1. So if c is greater than 1, c is up here, the y-intercept is up here somewhere. And there's a negative real solution, right? So that's good. So this is fine. But the question is saying only if. So can I find some c less than 1 where I get a negative solution? And I can, I think, right? There. Now there's an example where c is less than 1, and I have a negative solution, right? The solution is over here. So this is not okay. It's not correct. The equation has two distinct real solutions if c is greater than 1. So I want c to be greater than 1. This is only talking about c greater than 1. So can I find a place where c is greater than 1 and I don't get two distinct real solutions? Well, yeah, if I just shift this line up a bit to make it go up there, this is just an example of it working. But if I just shift that previous line I had up to there, then c is now bigger than 1 and I only have one solution. So this is not correct either. Now, the equation has two distinct positive real solutions if and only if c is less than or equal to 1. So now I'm looking down here. If c is less than or equal to 1, do I get two positive solutions? Well, here's an example of me doing it. But I can also find, and maybe you'll also think that, well, if c is less than or equal to 1, that's actually the only time you can get two distinct positive solutions. So this is only true if this. But what about just if? Like if c is less than or equal to 1, do you get two positive solutions every time? And the answer is no, right? This line here, we've already seen it. C is less than or equal to 1, and I only get one solution. So I don't get two distinct positive solutions. It's also negative if c is less than or equal to 1 every time. It is the only way to get to, but you don't always get to. So this isn't true either. And so none of them are actually true. Question number 12. This question makes you wonder, like, if you were taking year 7 maths, or if you were in if you were in year 7 taking maths, and someone showed you this question and were like, this is what you're going to be doing in year 13 maths, I feel like most of us would have just ran. Like, what is this? This is more writing than I did an entire GCSE English. Okay, how do you write a negation of a statement? Well, if you ever see the words for any, essentially you're going to write a statement where you're going to change a bunch of things. If you ever see for any, that changes to there is a, or there exists, or something like that. If you see there is a, that goes back to a for any, right? So these two things in a negated statement swap places. There is a swaps to for any swaps to there is a, and vice versa. If you see something like not, that changes to yes. And again, if you see one more for any, that goes back to where there is. So I'm going to try and write a statement that has the other stuff, the stuff that you actually think is important, like this stuff about integers k and stuff. That's just the fluff bit. What I'm looking for is there is a integer n for any k such that this is prime and there is an m that makes that true, right? Like I'm looking for a statement that basically says that. So it needs to start with a there is a n. So it's not any of the first four. So it's one of the last four. Then it needs to go into a for any k, such that for any k is these three. It can't be this one because that says and a. And we need a for any because that's the opposite of there is. So it's one of these three down here for any k's we've got going on along here. Then it needs to say is prime because that's the opposite of is not prime. So is prime is these two. Is prime, we can see at the end there. They've changed the order just because it makes more sense linguistically if they do. But look for the is prime, so that's one of these two. And then we're looking for there is an integer n, which is this one here. Because again, that's the opposite for any. So it's going to be that statement there. So those are your rules. For any changes to there is and vice versa. If you see a not or a is, then that changes to an is or a not and vice versa. Okay, question number 13. If tan of theta is greater than 0, then this is, okay, cool. So what's annoying about this question is that this student is a terrible mathematician because their working is so unclear such that every single step looks like it could be wrong, because it's just not clear what they're doing. So for example, now I know tan theta is sine theta over cos theta, that's fine. And they're saying tan is greater than 0, so cos isn't 0, which means dividing by this is fine. Now, where does this come from? Well, what they've done is they've times both sides of this equation by cos theta squared to make this into a tan cos, which they've then moved to the other side, and to make this into a sine cos, tan cos squared, I should have said, and make this a sine cos. And because this is bigger than 0, when you times this by cos squared, which is bigger than 0 because it's squared, this is still bigger than 0. So this is written terribly, but it's fine. This is also written terribly, and it took me a good while to work out what the hell they were doing here. But if you times sine cos by 2, what they've said in this first line is that sine cos is bigger than 0, if tan is bigger than 0, which is where they started. If you times that by 2, then that's still bigger than 0. And if you add 1 to it, therefore it's bigger than 1, because it's 1 plus something bigger than 0, which is bigger than 1. Okay, so that's where that comes from, which they haven't explained at all, but it's fine. It's technically a correct line. They just need to be more clear about how they got it. Now, they've turned 1 into sine squared plus cos squared. So this is the first line that is actually legible and a decent piece of maths, but they've done that. Then they factorize this. Again, this is clear. They've even said it factorizes, which is nice. So it knows what they've done, which is good. And now here's the problem, is that just because something squared is bigger than 1 does not mean that that thing is bigger than 1. Here's the example. So this false thing here is right at the end, and it's fairly obvious. You have to chunk through a bunch of absolutely terrible maths to see this very obvious problem. And the problem is that this is just not true at all. Question number 14. So triangle PQR, draw it every single time they talk about a shape. PR is 2, QR is P, and this angle is 30. And they're asking me about values of P for which uniquely determine this. So I'm asking whether this is unique. Now, if you search in my channel, I actually have a game show for this very type of question where I ask whether or not a triangle is unique. So yeah, I'd recommend you go find that. It's a fantastic video, if I do say so myself. I'm actually just going to do some sine rule on this because that's probably the quickest way of thinking about it. I could go on for half an hour about what I did in that video, but sine rule gets this done quite quickly. What I'm going to say is, if I call this angle down here y, I'm going to look for when y is unique. Because if y isn't unique, then this angle isn't unique. And if this angle isn't unique, you can imagine as you increase this angle, this length increases, and therefore this isn't unique. So I'm looking for when y is unique or not unique, because that makes this so, and therefore this so. And I'm chosen y because I can do sine rule on these 4 objects pretty easily. 2 over sine y is p over sine 30. I'm not sure why I put the signs on the bottom of this thinking about it, but it's not going to make a difference. Sine 30 is a half, p divided by a half is 2p, cross out the 2's to get, and then times by sine y, divided by p, and you get this. So sine y is 1 over p, and I'm looking for that to be unique. Like, I want this to be unique, because if this is unique, then this is unique, because there are 180 degrees in a triangle, and if this is unique, then this is. Because this can't change length unless this angle gets smaller or bigger and opens this kind of arc up longer or shorter. So I'm looking for this to be unique here. Now, when is sine y unique? Well, drawing sine between 0 and 180, I only need to do it up to 180, because that's as big as this angle can get, except it's not, and I'll explain that in a second. Now, where is sine unique between 0 and 180? Well, the only place, if I just, sine of 0.5 isn't unique. Sorry, sine x equals 0.5 isn't unique. You can either have 30 or 150, right? And sine x of 0.7 isn't unique. You can either have this or this. There is one unique value here, which is 1. Sine x of 1, or sine y of 1, I guess, if I'm doing it like this, has a unique answer of 90. So 1, if this thing here, if 1 over p is 1, then that's unique. And of course, that makes p 1. 1 divided by 1 is 1. So if p is 1, then we're unique. However, there are other ways to be unique here, because this angle here is 30, which means actually the biggest that this angle can possibly be is 150. Which means if sine of y was like 0.3, you can have this angle, and you can't have this one, because you can't make y bigger than 150, because that breaks the rule. So actually, if sine of the angle is less than 0.5, and sine of the angle is 1 over p, so if 1 over p is less than a half, then I have a unique solution, because I can't match it with anything over here. And of course, you can sort this out, times by p, times by 2, and you want p to be bigger or equal to 2. So either p is 1 or p is bigger or equal to 2. That's when you make a unique triangle. Question number 15. Getting through it. Let's keep going. Given that you've got some function, now this is a cubic function. It's a positive cubic, which means it starts down there and ends up there, and it goes through the point 2 and the y-intercept. So it goes through there. You're told it has 3 distinct real roots, so it looks a bit like this. So you have 1 root, 2 roots, 3 roots. And the way to know whether a cubic has 3 roots is one of its turning points has got to be above the axis, and one has to be below, because that way it has to cross the axis another 2 times to get between the turning points, right? So that's when you have 3 roots. Now, what's this equation look like? Well, this is just when I add 1 to the function, so the function shifts up by 1. Does that necessarily have 3 distinct roots? Well, no, because if this point down here is a half, or minus a half, I should say, when I move this graph up by 1, this turning point goes all the way up here. And suddenly the graph goes up here, turns here, and goes up here, and you only have that one solution down here. So that's not always true. When you move the graph side to side, of course, you still have 3 roots. Like, this just moves the graph 1 to the right, oh, sorry, 1 to the left, doesn't it? But you're still going to have 3 roots, so that's fine. This one's the more complicated one. First, I'm going to flip the graph in the y-axis. So, boom. Nice. Enjoyed that. Then I'm going to take away 1. Now, it's tempting to say the same thing as we did before and say, oh, but what if this is less than 1 and therefore it moves down here? But look, the y-intercept is at 2. So this turning point must be, even I've exaggerated it a lot, but it must be slightly above 2, right? It must be at least a little bit above 2, which means when you take away 1, this turning point is always still above the line, which means you will get 3 roots here as well. And the answer is 2 and 3, sorry. Okay, question number 16. Another arithmetic progression question. What I'm going to do, again, I'm seeing this, which of these must be true. I'm just going to come up with examples. There's a sequence with arithmetic progression. There's another one. There's another one. They're all a bit different, so hopefully they're all going to kind of, hopefully, contradict some of these between them. Now, the median, let n be a positive integer. Let's just choose n to be 1 to start with. If the median of the first term is an integer, now it is, because these have to be integers, which of the following is true? Now, if I chose n to be 1, then now n is 3, n plus 2 is 3. And the median is still, well, it's just in the middle of 3 integers, so it's just an integer, right? So that seems true. So I'm going to say that's fine. And actually, I can prove it as well. There was a bit of a spoiler there, but I can prove this one as well. Like, for example, if you choose n to be, let's say, 2. Well, if you choose n to be 2, then looking at this one, the median isn't a whole number, but it says if the median is an integer, so I can ignore that case. So if I choose n to be 2 here, the median is 2. And then if I add 2 to that and choose n is 4, the median is 4. And you might think, well, that's not completely obvious that that's always true. But the reason that it is always true is because you're adding up by a constant number every time. And whether you add an even number on every time or whether you add an odd number on every time, after you do that an even number of times, either 2 times or 3 times or 4 times, you always add on an even number in total. So if you notice, when n was 1, I added 2 up to get 2 differentials, which means I'm adding an even number in total. And likewise, if n is 1, despite the fact that the differential is odd, when I move to n is 3, because of n plus 2, the differential there is even, which makes the median even, because the median you can kind of think of as being obviously the average. So if the average between them is even, you divide that by 2, it's just a whole number. So it's a little bit difficult to think through this entirely, but the fact that I can't find a counterexample, the fact that a counterexample doesn't work, maybe by question number 16, you just think, well, because there's no counterexample, I'm just going to assume that it's probably correct. And now I can find a counterexample to this very easily. Again, choose n to be 1 here, say, the median is 3. Double it, choose n to be 2, the median is 2.5. So that's clearly wrong. And this is what I'm saying is maybe you actually just try and get through this as quickly as possible, find the obvious counterexamples, and then just assume the other things are true, which is not good maths, but it is much quicker and might enable you to answer another question afterwards or instead. And it does also, like, getting rid of the easy counterexamples does make your guess much more accurate as well. Let's say you leave it between two options. That gives you a 50-50 chance of getting it right. Now, again, you can think through this one. Now, this ends up being true as well. Essentially, what you're doing is you're taking every other term, so 3, 7, 11, and finding the median of that. And likewise, for the same reason that this had this kind of even difference going on when you double out the terms, because whether you double an even difference or an odd difference, the difference of that double is even. These both end up being fine. But again, a little bit difficult to think through that. So maybe it's best just to come up with the counterexamples, eliminate all the ones that can't be true, and then put down your best guess, and then move on to a better question, which is not this, but maybe a better question like the thing that comes afterwards. Again, maybe I didn't explain that properly. The reason that I'm not talking about this in huge detail is because I'm thinking about making videos just about this kind of idea and coaching through this idea, and now isn't the time to do that because this video would just be unnecessarily long and difficult to find and get through. So I'm just going to move on. Okay, so it's defining this thing square sum if it can be written as the sum of two integers. Now notice integer doesn't eliminate 0. So then it goes through this whole thing about awkward if it has a remainder 3 when divided by 4, so 23 is awkward. And then your square sum, apparently, if for each of your awkward prime factors, when you make the prime factorization, the awkward primes turn up to an even power. So whatever this number is, and I can't bother to work it out, this is square sum because this isn't awkward, so it doesn't matter. Like, we're not talking about non-awkward primes. This is awkward, as it was given to us, and it has an even prime, an even power, sorry. So this is square sum. This isn't because, again, I don't care about this because it's not awkward. I do care about this because it is, but it has an odd power. So this can't be square sum. It's not asking you to prove that. I imagine the proof, because it was done by Fermat, is probably quite difficult and above the level of a TMUA paper, but it's just stating that that's how it happens. So every square number is a square sum. Now that is true. And this example makes that very obvious because you can just use 0. And you can just use the square as just the square plus 0. So that's fine, that's definitely true. Now this is going to be the more complicated one. I'm going to do something that looks very university level here. I'm going to say n is just a bunch of primes multiplied together to a bunch of different powers. So for example, with this one that they gave us, the first prime is 5, p1, and then m1 is 1. And then the second prime is 23, and the second power is 2. And then there's nothing after that. But I'm just going to say n is some number with all that, and I'm going to say m is also some number that does that, but with different primes and different powers. Now, when you multiply these together, now, if any of these primes aren't awkward, I do not care about them, right? Like, if this isn't, like with these 5s here, I didn't care about the 5s at all because I'm only interested in whether the thing has awkward prime factors. So if any of these primes are not awkward, I don't care about them. Now for the primes that are awkward, let's say that P2 is prime and awkward. It's definitely prime, but let's say it's awkward and has an even power. Now it must have an even power because n is a square sum. So any awkward prime that it has must have an even prime. Now let's pretend that Q3 is the same prime as P2. Now, because m is square sum, if q is awkward, then this also must be even. And when you multiply n and m together, you end up adding these powers together if the prime is the same. And when you add an even to an even, you still end up with an even. And so that prime that was awkward is still going to have an even power. And likewise for any other primes that are awkward and match. The primes that aren't awkward, whether or not they match with anything else, is irrelevant because the power on an awkward prime is completely irrelevant to this question. To just give you an example of what I was trying to say there, let's take these two. where I've got 5 to the 1 and 5 to the 23. So P is 5, P1 is 5, M1 is 1, P2 is 23, M2 is 2, and then there's no more primes. And likewise for this. If I multiply these together, I don't care what happens to the non-awkward primes. Like this becomes a 5 to the 3 when you times these together because you add the powers. This becomes a 21, so I don't care. These aren't awkward. But this one, which has an even power here and another even power here, adds the evens to make another even, and so this is still a square sum because its only awkward prime is still an even power. So this is definitely true. And I'm looking for the not true, remember. This one here, now, if n is square sum, if nm is square sum, now let's just take nm to be, let's just take n, sorry. Let's just take n to, sorry, I thought I was going to do it in a different way, but I'm going to do it like this instead, apparently. Let's take n to be the example they gave us, which is square sum, because this is irrelevant, this is awkward, has an even factor. Now let's just take a to be this, and let's take b to be this. Now, when I multiply a and b together, notice I make this square sum number n. A times b is n, because you just got 1 5, and then you got two 23s. But neither a or b are square sum, because their awkward prime, their only awkward prime that each of them have, is not an even power. So this is not true. I don't know why I chose a and b instead of just calling this n, m, and calling this n and m, but I hope you get what I was talking about there. Now, I found the not true one. There's no option to say more than one is untrue, so I'm just okay with keeping this. D, I don't really need to check, but just for sake of completion, what this is talking about is that if you have some number that's not square sum, like this one here, there's some number you can use which makes this into a square sum, and that's fairly obvious. Basically, it's saying whatever awkward primes you have that are to odd powers, you can fill them up with those awkward primes to make them all even. So for example, I can multiply this by 23 to make it square sum. So yeah, this is fairly obviously true as well, but it's irrelevant because I already found that's not true. Question number 18. This is quite a tough question as well. I think the only way to do this is to probably draw it. So here's a function. It's a polynomial, so it goes up and down a bit. Let's call this a and this b. Now, if this is a, I did this a bit before, but if this is a, then this is defined to be f of a. And if this is b, then this is f of b. Now, a plus b over 2 is, of course, in the middle of these two things here. And that means f of a plus 2 is in the middle there. A plus b over 2. Now, where is f of a plus f of b over 2? Well, that's, looking at this axis, that's the mean of this input, this output, and this output. So if I add this and divide by 2, I end up right in the middle of these two things, which isn't necessarily where this comes out. And in fact, where it is if you draw a straight line from the two functions that you're averaging, outputs, sorry, that you're averaging, it's the middle of those, right? So it's just there, just below in this case. And now this is very much like when you do trapezium rule to estimate area, in the sense that for this one to be above this one, you need to have a convex graph. And for this one to be below this one, you need to have a concave graph, which is what they want. So I need my graph to be concave. So I need it to be looking like an exponential rule. It needs to look like a bit of an exponential, right? And that's going to give me this is bigger than this. So how do I have like a concave graph? Well, that's when the second differential is always positive. Because if the second differential is positive, that means that the gradient is always increasing, right? Because this is kind of the gradient of the gradient. If this is bigger than 0, then the gradient of the gradient is always bigger than 0, which means the gradient is always increasing, which means it's that convex idea. The gradient is getting steeper and steeper and steeper. So it's this one here. Quite a difficult question to get, though, I think. But yeah, let me just charge up my computer because I'm worried it will go off with 2 questions to go, which is not going to be fun. Sorry for the delay. There it is. Next question, question number 19. Oh, skip straight to 20 apparently. Question number 19. 3 real numbers satisfy that. Now notice real, not whole, but real. Which of the following must be true? So again, it's asking must be true, so let's just find some counterexamples. So here, I kind of see when I'm looking at this that, okay, I want this one to be smaller. If I just make x really, really big, then not only does this make this big, but it also makes this small. So I'm going to choose x to be the terrifyingly large number of 10, and then just y and z to be these. And when I put this into here, this is 2 to the power minus 7, and this is basically 2 to the power 7, so this is clearly bigger. So that's not true. So I'm going to get rid of this. I flashed up a joke there by mistake. Oh well. This one, I'm going to do the same thing. If I make x really, really big and y much smaller, then this is going to be very big. And it's probably going to be bigger than 2. So I'm going to choose x to be 22, y to be 3, and z to be 2. I'm just choosing 22 because I don't want to do the same thing again. But that makes this statement here. And this is, yeah. C looks a bit harder to sort out. Now D looks a bit like B. So I'm going to try and sort out D because I feel like I have a good chance with it because it looks pretty much like this. Now looking at this, I need to make this less than 2 to find a counterexample to this. So I need to make this very small. Now what I can do here, after a bit of trial and error, is if you make x really big and y basically the same, but just a tiny bit smaller because you have to, and z very small, then you end up with this statement. Now the thing about this is that this is a massive number, like enormous, and so is this. In fact, they're so enormous that this number basically doesn't matter. Like this is basically just z to the 100 divided by z to the 99.9, which is z to the, you then take away the numbers to get this. And like, I actually don't know whether z to the 0.1 is bigger than 2 or not, but what I do know is that I could make this power arbitrarily small just by choosing this to be, say, 100 and this to be 99.99999, right? And then I basically have z to the 0, which I know is less than 2. So I know this isn't necessarily true, which means that this is. Good. Question number 20. Okay, so the first thing I'm thinking when I see roots is that square roots are defined to be positive. So the square root of anything is defined to be positive or 0, which means p has to be positive or 0. So I think I wrote that there, but it's not coming up yet. Hope it comes up soon. It doesn't. Okay, but p has to be positive or 0, I think. So this seems like a good shout, but it does. I haven't eliminated like these here. But this seems like a good shout, but let's keep going. I'm just going to take away root x from both sides, then I'm going to square both sides. Now this squares easily. This makes sure you square by expanding out the brackets properly, and you get this. Now the x's nicely go away here, and now I'm going to move this to the other side and move the p over. And now I notice I have a p across every term. Now, if p was 0, if this was 0, then I'd have root x plus root x is 0. And that's fine as long as x is 0. So p equals 0 is a solution if x is 0. And the fact that I've said that, remember way earlier when in that wrong question they divided by a factor and they lost a solution. I'm going to divide by a factor here, but I'm going to do it correctly by saying, actually, I have a solution here, and now I can divide by the p and look for more. But I've made a note that I do have a solution at p is 0, x is 0, because root 0 plus root 0 is 0. So this is fine. This is a solution. Now, what about this here? Well, again, notice this thing at the top here. This is defined to be positive. I mean, root x is, and then when you times it by 2, that's still a positive, which means this must be positive. Which means p can't just be any positive number. P has to be bigger or equal to 1. Because this has to be positive. And I think it's fairly logical that whatever I make x, now I have to choose x to be positive because otherwise the original statement doesn't work. You can't take a square root of a negative according to this because of this word. So whatever I choose to be x, this just ends up being some number. And I can always find a p that just takes away from 1 to make that, right? So as long as p is greater or equal to 1, this is positive, and I think I can always find a solution. So I have a solution to p is 0, where x is 0, and I also have a solution for any value where p is greater or equal to 1. And that will be my answer. And that's the entire paper. Thank you for listening.